Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 4, Lesson 2. We are going to continue talking today about circuits that have resistors in them. So super simple. If I have a battery connected to a resistor, current is going to flow counterclockwise. Current's going to flow this way. I is the letter we use to represent current. And so as the current flows around in the circuit, we have a gain in potential as we cross the battery, and we have a loss in potential as we cross the resistor. And in this super simple circuit, however many volts we gain going across the battery, we lose that same number of volts going across the resistor. And that's because at any given location, the potential here, or the voltage, has to be equal to the potential here, because I'm pointing at the same place. So if I gain a certain number of volts, I have to lose that same number of volts before I get back to my starting point. So we can talk about the current through the resistor. We can talk about the potential difference across the resistor, and we can talk about the resistance of the resistor. And I said those three phrases and used those prepositions last time, the preposition across, through, and of. Because the only thing that makes physics more fun is when we can talk about physics and grammar at the same time. All right, anyway, so the current through the resistor, the potential difference across the resistor, the resistance of the resistor are three things that we would love to talk about: current, potential difference, and resistance. Well, it turns out that there is one additional quantity that we can calculate for a resistor. And the reason we're going to talk about that is what happens as current is flowing. Well, what's really happening is, nothing goes in the direction of current. Electrons would flow this way. Electrons go that way. So as electrons go through the battery, they scoop up energy. And then as they travel across the resistor, they dump out that energy. So charge carriers, charged things that move, are a way of transferring energy from the battery to the resistor. Now, maybe it is simply just a resistor and a portion of wire of high resistance so that it's hard for the electrons to get across there. The electrons are losing their energy. What does that energy turn into? It could turn into heat and light. So if it's a light bulb, it's emitting light, and that's energy. But light bulbs also tend to get hot, so it's also emitting heat. If it's a light bulb, the light is useful and the heat is waste. But what if it's a toaster oven? Well, those things in your toaster oven are just resistors, and they also emit heat and they glow because they're emitting light. So in that context, the heat is useful and the light is waste. So what is useful and what is wasteful is in the eye of the beholder. But what's happening is that energy is coming out. Energy comes out in the form of heat and light, or if I have some other kind of device like a blender, then it would come out in the form of mechanical energy. The big idea: charged particles pick up energy, charged particles drop off energy. And so we could talk about how much energy comes out, but the longer this circuit runs, the more energy is going to come out, and I don't know how long I'm going to run the circuit. So what we're actually going to measure is the rate at which the energy comes out. Rate of energy, that should be sounding and feeling familiar. The rate at which energy comes out or is released. And that the rate at which energy comes out is going to be measured in joules, the amount of energy, divided by seconds, the time it takes the energy to come out. The unit for this rate is joules per second. How many joules of energy per second are released? Do you remember this from our previous, not our previous lesson, but our previous class, the first year, AP Physics 1? The rate at which something happens with energy is called power. And a lot of people use the word power to mean a lot of different things, but in physics, power is the rate at which energy happens, the rate at which energy is gained or released or transferred or converted. It's the number of joules of energy that do something each second, and that is power. So power is abbreviated with a capital P. The unit for power is, well, there it is, joules per second, or the watt. So 1 joule per second is a watt. What is it really in terms of our base units? Well, a joule, you might remember, is a kilogram times meter squared over seconds squared. And then when I divide that by seconds, it's seconds cubed. So joules per second, or watt, or kilograms times meters per second squared. All of those are units for power. So there you go. I'm just looking at my notes. So I defined power, and I reminded you of the unit, and I said what it means in a circuit is that energy is coming out. So I, V, R, and P, we might also wonder what the power is. And it turns out that the power for a resistor is equal to IV. Why does that make sense? The unit for current is coulombs per second. And the unit for voltage, the potential difference across there, is joules per coulomb. Did you notice that I said coulombs per second, but I didn't write an S when I said that? Coulombs per second, joules per coulomb. So there's a potential difference. Every charge that goes through there, there's a certain number of joules for each coulomb of charge that crosses. And then the current is how many coulombs cross per second. So that comes out to be joules per second, or power. So power is the product of I and V. Power is IV. Here's a fun little kinesthetic thing to do. Can you hold one finger up on one hand and 2 fingers up on the other hand and go pow? And this looks like an I and this looks like a V. Power. Power is IV. So anyway, just do that, and that's your kinesthetic way of remembering. Power is IV. So I'm going to write that on the next page. Power equals IV. But do you remember that we said V equaled IR? That was Ohm's law. So I can also say power equals I. Instead of V, I can write IR. So power is I squared R. Or, since V equals IR, I equals V over R. So instead of P equals IV, instead of I can write V over R. And I can say power is V squared over R. So 3 different equations for calculating power. If I have a resistor and I know the current through it, the potential difference across it, and the resistance of it, I can use any of these 3 equations to calculate the power, the number of joules per second of energy coming out, the rate at which energy is released. But often you don't know I and V and R. But if you know any 2 of them, I and V, use that. V and R, use that. I and R, use that one. So whatever you know about a resistor, the current through it, the resistance of it, or the potential difference across it, if you know any 2 of them, you can calculate the number of joules of energy that are released there each second. And I just wanted to remind you, this to me feels a lot like what we said about capacitors. Remember when we had a capacitor and we talked about the energy stored in a capacitor? Remember we talked about that energy stored in a capacitor? And we said there were different formulas that we could use. And so one of them was energy stored was QV over 2. Does that sound familiar? And then because Q equaled CV, we also could have said energy equals, instead of Q, I'll write CV. CV, V over 2, 1/2 CV squared. Or because instead of replacing Q, I could replace V. V is Q over C. Q times Q over C over 2, which is Q squared over 2C. So any of those three formulas would tell you the energy stored in a capacitor. And that's not what we're studying today. But this lesson feels very familiar to me, or this lesson feels familiar because it reminds me of this lesson. So feel free to set those next to each other in your notes, recopy these onto this page if you want. And it was a lovely review of what power is. Okay, and now all I'm going to do is a couple example problems for you. So here's an example problem. Let's see. Let's do this one that's labeled number 32 from chapter 17, section 8. If electrical energy costs 12 cents per kilowatt hour, we'll talk about kilowatt hour in a minute, how much does it cost to burn a 100-watt light bulb for 24 hours? So let's do that first. A 100-watt light bulb for 24 hours. What is a kilowatt hour? 1 kilowatt hour. Kilo means 1,000. So 1,000. Watt is a joule per second. And an hour is 60 minutes, or 60 times 60, 3,600 seconds. 1 kilowatt hour is 1,000 watts, joule per second, times 3,600 seconds. A kilowatt hour is really 3,600 times 1,000 is 3,600,000 joules. A kilowatt hour, believe it or not, is an amount of energy, and it's 3,600,000 joules. And this problem said that electrical energy costs 12 cents. Costs 12 cents. It costs 12 cents to buy that many joules. It costs 1.2 cents to buy a tenth of that. It costs 24 cents to buy that times 2. All right. Now this says I'm going to burn a 100-watt light bulb for 24 hours. A 100-watt light bulb for 24 hours. Now 100 watts is 100 joules per second. So I've got 24 hours. 24 hours. If I could convert that into seconds and then multiply by this conversion factor, I can find out how much energy that is. So watch, 24 hours, 1 hour is 60 minutes. And 1 minute is 60 seconds. This is how I'm converting 24 hours to seconds. People often wonder, well, why did you multiply by 60 instead of dividing by 60? Wrong question. I had hours here in the numerator, and I put hours in the denominator so I could cancel them. I put hour on the bottom, and therefore minute had to be on the top. The reason 60 was on the top was because 60 minutes is equal to 1 hour. But I don't like minutes, so I wrote minutes down here so I could cancel, and I put seconds up there. Now, all my units have canceled. I've turned 24 hours by doing this multiplication into seconds. And now I can multiply by this. And I'm going to write 100 joules over seconds because I want this seconds and this second to cancel. Now I have how many joules? And I know that 3,600,000 joules cost 12 cents. And again, the way I knew to write joules in the denominator and money in the numerator was so that things would cancel. And now this is going to tell me how many cents that costs. All I have to do now is stick this into the calculator. 24 hours times 60 times 60 times 100 divided by 3,600,000. 2.4. 2.4 cents. Goodness gracious, what? That's not very expensive. Did I leave out the 100? Let me try it again. 24, 60, 60, 100, 12. Well, I might have left out the 12. 3,600,000. So when I have a bunch of stuff in the calculator, I often enter it a couple times just to make sure I didn't leave something out. 28.8. Still doesn't cost very much. For a 100-watt light bulb for 24 hours costs a little more than 28 cents. This, to me, reminds me of the stoichiometry problems that we did in our chemistry class, when they said something like, if you have 6 grams of copper reacting in this reaction, how many grams of, one of the products can you get? It feels like that. So this was what we started with. We had a certain amount of time, and that was going to correspond to a certain bill that I'm going to get. And each of these things that I multiplied by is called a conversion factor, where the numerator and denominator are equivalent to each other. All right, that was letter A. And then letter B said, how much does it cost to operate an electric oven for 5 hours with a current of 20 amps at 220 volts? So 20 amps, 220 volts. 20 amps, 220 volts for 5 hours. 20 amps, I'm making sure I copy the problem down right. Yes, 20 amps, 220 volts. So power is IV. So there's the current in amps, there's the voltage in volts. 220 times 2 is 440. 20 times 220. So that's 440 with one more zero. 4,400. 4,400 watts for 5 hours. So I don't really need to write it all out. I'm just going to compare it to this. Instead of 24 hours, I'm going to write 5 hours. And then I'm going to do the same. There's still 60 minutes in an hour. There's still 60 seconds in a minute. And instead of 100 watts or 100 joules per second, there's 4,400. And it still costs 12 cents for 3,600,000 joules. And I'm writing this all down and you're not seeing it. But it's all the same parts of the equation. And we could go through and do that multiplication. I'll leave that for you to do. Make sense? All right, we're going to do one more example problem, and then we'll be done. The next example problem I'd like to look at is this one right here. A motor draws a current. So the current is 1.75 amps. And the potential difference is 120 volts. So P power is IV. The output power is 0.2 horsepower. So 0.2 horsepower is equivalent to a certain number of watts. We'll look at that. First of all, I am going to say, hey, what is the efficiency? Let's do letter B first, because that's interesting. 1.7 amps, 1.75 amps, 120 volts. 1.75 amps times 120 volts. This is the current. This is the voltage. So this is going to give me the power in watts. I know I could do this in my head, but I'm not going to. 1.75 times 120 is 210. 210 watts. Now, they told me the power is 0.2 horsepower, which is just them being ridiculous. There's no reason they should have told us that. So I'm just going to ask Siri to convert that for me. Convert 0.2 horsepower to watts. And it's 147. There we go. Wasn't that easy? 147 watts. I don't know why people who write textbooks want everything to be confusing. So this is how much energy I'm expecting to come out. This is how much energy I'm actually getting out. It says here, the output power, the number of joules per second that are actually coming out, is 0.2 horsepower, or the rate at which energy is coming out is actually 147 watts. So the efficiency is just 147 over 210. This is the rate at which the energy is coming out. This is zoom in, zoom out thing. So sorry. This is the rate the energy is coming out. This is the rate I was expecting it to come out. So this is going to give me my efficiency. 147 over 210 is 70%. All right. Now let's look at question A, which said, at a rate of this per kilowatt hour, in other words, 6 cents per kilowatt hour, what's the cost at 4 hours? Oh, wait a minute. That's that same problem again. Right? If I'm now going to run it for 4 hours, and they're only going to charge me 6 cents per kilowatt hour, right? So instead of 24 hours, it's 4 hours. I'm going to multiply by 60. I'm going to multiply by 60 to convert from hours to minutes, and then from minutes to seconds. And then watts is really joules per second. So times 100. And then they're charging me 6 cents per kilowatt hour instead of 12 cents. So you just do that multiplication. So 3 of those problems in a row were all that same conversion. I mean, I guess the idea is you should know how to convert from hours to seconds. You should know that a watt is a joule per second. So if I know the power, the number of joules per second, and I multiply that by the number of seconds, that gives you the energy used. So that's important. They're saying energy is equal to power times time. Right? I took my energy used, and then this is the rate at which they were charging me. It was the price they were charging me. So if energy is power times time, oh wait, power equals energy over time, and that takes us back to the very beginning. What is power? It's the rate at which energy is exchanged, the number of joules per second. So we've come full circle back to defining power. If power is energy over time, energy is the power times the time. that's where I'm going to leave you. I hope you have a great day. But whatever you do, don't break the laws of physics.